Welcome back, everyone, to the eCoreAcademy e-learning platform. Today, my name is AJay Raj, back with yet another geometry video for you all. Today's lesson topic is all about volumes and surface area of spheres. But before we jump into that, please make sure to smash that subscribe button, hit that like button on this video, as well as turning on post notifications by hitting that little bell icon right next to the subscribe button. All three of those things are very greatly appreciated. As I was saying, today's lesson topic is going to be focusing on yet another three-dimensional topic. Right now, we're moving into a bit of basically a transition. We're transitioning from 2D and planar and coplanar objects over toward three-dimensional objects. So we're changing our dimensions from two-dimensional to three-dimensional. We started off the year by looking at lines, trying to correlate algebra to geometry, which is basically your one dimension. And then after that, you're going to two-dimensional, which is basically correlating with figures, two-dimensional figures, which geometry is very keen on, as well as three-dimensional figures, which we're actually entering into now. We're not going to look at very extensively with three-dimensional figures as in correlations-wise, but we will refer to just about every single type. So your complex figures such as dodecahedrons, all that sweet stuff, all the way to the, your basics like your triangular prisms, and of course, as we can see today, we have our spheres. And I did previously make a video on our cones and cylinders. So order of that is pyramids, cones and cylinders, and then spheres. So today's lesson topics theme is to look at and discover what are some properties of spheres. So we're going to be looking at spheres under a magnifying glass, trying to magnify on the different properties that they have and some identifications that they have as well. And we're also going to discover what are their volume and surface area formulas. As we know that it's very important to describe our formulas, looking at the fundamentals and basics of three-dimensional figures before we actually go into depth in identifying complex figures. And that's more what you'll look at later on in higher level math. You'll kind of refer to it in pre-calculus and calculus, and later on into higher level math and multivariable calc. Everything's related to relative figures can be written in algebraic terms, so it's important to know this. So let's look at spheres today. Hypertense to focus on spheres. So let's look at parts of a sphere. So let's start off with the parts of a sphere, and this is part one, of course. And like I said, let's look at the parts of a sphere. And if we're looking at spheres, you might relate to a two-dimensional figure. As you can tell, a lot of three-dimensional figures are actually founded and based off of two-dimensional figures given. That's how it all works. Lines create two-dimensional figures, and some sort of two-dimensional figure base, it creates your three-dimensional figure. So, of course, you're going to have a 3D figure that's going to be based off of a 2D figure. And if you think of a sphere, you're probably already thinking of a circle. So a sphere is heavily founded off of a circle. So circles are the foundational shape for spheres, as spheres are inclusive of infinite amounts of circles. So this means it's only involving with circles, unlike cylinders, which are, circles and a rectangle, and even cones, which is a third of a cylinder, so the same exact properties. And sometimes if you're looking at it straight on, it looks like a triangle, but this is solely based off of the circle, and that's what correlates it very well with the 2D objects. And there's actually much more that you can actually do with the sphere just because of that. So it's inclusive of infinite amounts of circles, covering all possible planes, sharing a common central point. Now we know that circles are two-dimensional objects. That means they're located on a singular plane. A singular plane is your two-dimensional outlook. And basically what a sphere is you're taking that given circle, any given circle on any plane, and all you're doing is rotating it along your x-axis, which is this way, and y-axis, which is this way. And when you do that, when you rotate it along those axes, you're looking at all the infinite amounts of planes that you can create a circle. And once you do that, you'll actually come up with your 3D object of a sphere. And the sphere, like I said, is going to have a common central point. That's all going to be similar to the very given circle. And then, of course, you have the diameter, radius, and center of a sphere that are consistent to that of a circle, because, we have our diameter of a circle, radius of a circle. Diameter is the length across from a circle. Radius is the center of a circle, like I'm showing you here. Blue is the diameter, so it's the entire length of, your given circle, the central circle. The great circle is basically the center of a sphere, so I'll write that. Great circle. Central circle of a sphere, And of course, it's going to be the circle it's going to be the circle that wraps around your center here of your sphere, and that's the same distance from all points on your sphere are going to be the same distance from the center, just as it is from the circle, a two-dimensional figure to the circle. And then you have your diameter here. Diameter is the length across your great circle, and that's going to be consistent from any point, say for example, across this great circle, or across this entire sphere. So any 2 points on the sphere will also be equivalent to the same diameter of this center circle, as well as the radius. So that goes for the same from the center point to any other point on the sphere. Everything works in the same manner. Let's look at parts of a sphere, part 2. And now let's look at the center of a sphere. So let's look at what spheres are, and then let's identify the center and start building up off of there, and then get into the surface area and volume formulas. So the center of a sphere. So let's look at the sphere first before we actually identify the center. So a sphere is a figure in space made up of all points equidistant from a given central point. And that's similar to a circle, but not on plane. Then again, it's a three-dimensional outlook. That's the only difference between a circle and a sphere. They're so similar, but it's just the dimensions that they have. But they're all one's founded based off of the other. The sphere is founded off of the circle. So a sphere is a figure in space made up of all points equidistant from a given central point. Now, if you look at a center, it's going to be all given points on the same exact plane that are the same distance from that given point. But for a sphere, it's going to be anywhere. So it's going to be any point in space instead of any point on a plane, because it's three-dimensional. It's all possible planes. So you can have a point and on a three-dimensional outlook, and you could connect it to all these different points, and that's what defines a sphere, just as a circle is defined by a central point on a plane. And it's similar to a circle, but on a plane, like I said, but it's three-dimensional. And then, of course, you have your center, and it's the point to which all points on a surface of a sphere are equidistant. So if you're looking at all the edges of your given sphere here, and you're given your center here, it's your central point of your great circle, this central circle here, it's going to be equal from all points of your sphere. So any point on your sphere is going to be the same distance. And then again, that is the same thing as saying your radius. This is going to be your radius. So you can draw all of these points. Same thing with diameter. Your diameter is always going to be the same, and your diameter is basically twice your radius going across this entire sphere. So those are some simple definitions. Now let's move on to the volume of a sphere. This is going to be a bit of a quick lesson, but I will be going in higher depth with the sphere. I wanted to separate these two so that you guys get the fundamentals, and then, of course, we can move on to what's already expected in the next video. Get a higher pace with this. So we have the volume formula of a sphere. The volume formula of a sphere is 4/3 pi r cubed. And all of these terms should be familiar already, because these actually correlate to that of a circle. So the equation is derived from the volume of it should say area, from the area of the circle, but the radius is being cubed and multiplied by 4/3. So if you look at the area of a circle formula, it's going to be pi r squared. Now that's very similar to this given here, but in this case, it's going to be pi r cubed. So you're going to be cubing your r value. So this is going to be cubed, and you're going to multiply an extra 4/3 to that. Now, how does that actually correlate? What sense does that make? Well, what you're basically doing here is you're changing the dimensions up. So if you're given your radius and you're squaring your radius is a given line. Like I said, it's a one-dimensional figure, so it's a one-dimensional outlook. So your line is one-dimensional. Now, if you want to, develop that into a two-dimensional value, you're going to square that value. So it's going to square your line to get some sort of two-dimensional value, and that's going to be your area. It's going to be a two-dimensional figure, such as a circle. But even furthermore, you're going to now cube that value, cube that given line in order to get a three-dimensional value. That's how geometry works with your given base units, such as the radius with the circle. Perfect example to start with. Of course, pi will stay consistent because that's the ratio that you will always keep consistent with your two-dimensional value. The only thing you're changing is your cubic value here. And then, of course, you're multiplying it by 4/3 because that conversion will not actually equal a given sphere. It's going to equal it's going to equal about 2/3 or a little bit more than 2/3 of your given sphere. That's why I'm multiplying it by 4/3 to multiply along with your pi value. So that's how it works. So if we're given our sphere here, I'm going to give you an example. All we actually need is the radius, just as you would need for a circle to discover the volume of this sphere. So we're given that our radius is 4, here. So let's look at this here, and we'll say that I'm going to put everything in terms of pi, but I will multiply by 3.14, which is the closest approximation which is the most common approximation for pi, not the closest, but the most common. Because pi is irrational, it does not ever end. So we'll plug this in. So we have 4 here. So we know that's our R value here. So we're going to use this equation. So 4/3 pi R. All right, let's plug in our value this time. I want to keep this short. So 4/3 pi, and then R here is 4. So 4. And we're going to cube that value. So let's do order of our operations. We'll cube first. So 4 cubed is 4 times 4 times 4, and that's going to be 64. So 4/3 pi 16 times 16. We're going to multiply 16 by 4/3, and that's going to be 64 divided by 3. And 64 divided by 3, we're going to leave that as a improper fraction. So 64 divided by 3 pi. However, if you did want to simplify that, it would be 21 and 1/3 pi. Because it cannot be simplified, I like to leave it like this as a common fraction. However, you can leave it as a mixed number, not very common because you're leaving this pi value alone. But if we were to just, multiply that out, we would want to keep this consistent as 21 and 1/3 pi. But for the next problem, I'm going to be showing you what if we had an approximation to 3.14. So we're just going to leave this in terms of pi. So this is our answer here, both of our answers here. 64/3 pi. Let's move on to the next problem. And now let's look at surface area, our last part. And then I'm going to add a little bonus part, a little bit of more heightened enrichment topic. So let's look at the formula for surface area. The surface area of a sphere is 4 pi r squared. Now that's very common to your area of a circle. So the equation utilizes a circle that can cross through the center and touch all two-dimensional parts of the center. And also the surface area is smooth. So what I'm basically saying is you're going to take your center circle, which is your great circle here. So this is a circle that I'm going to outline right here. It's this great circle here. And also what you're going to do is you're going to look at this value here. You're going to take another circle and you're going to draw it through the center of the sphere. And now that you've done that, you can draw another circle here. It crosses through here. It's almost like I'm making a giant atom here. And a last one here. And so once you've done all of those, what you can basically see is that I'm making a giant grid here. This giant grid that's going across in this asterisk way. And those are 4 circles joined together. And what they're doing is they're touching every single bent angle of the circle, meaning what I'm basically drawing here is this. If you're looking at this at a two-dimensional view here. Now, these are like an asterisk here. If you have this asterisk here, you can basically draw a circle by connecting all those points. That's basically what this is doing here. It's utilizing that in order to cover the entire surface of this given circle, of this given sphere. And of course, our surface area is the distance all around the outside of your sphere. And surface area for a sphere is going to be smooth because it's going to be rounded completely, no jagged edges. That's the property of the sphere. And that's also a property of a circle. A given circle, that's what creates this property of the sphere. Now I'm going to erase this here, try and keep some space here. So let's look at a problem here. So I'm going to give you a radius because then again, that's all we need. I'll keep it consistent as a radius of, actually, let's use a radius of 3 this time. Let's use a radius of 3. So that's our radius of 3. And if r equals 3, we're just going to plug that into our equation right here. So 4 pi and 3 squared. Now we're going to simplify 4 pi times 9. And that equals 36 pi. Then again, if you want to simplify that to 3.14, round that to 3.14, we can multiply 3.14 by 36. 4, 2, 6, 8, 18, 0, 2, 1, 3, 0, 1, 3. So it's going to be 113.04. It's going to be 113.04, let's say inches in this case. Inches. And that's going to be inches squared, but if you're looking at volume, that'll be inches cubed because this is area. All right, now let's look at this bonus topic that I have here. It's not necessarily correlating to spheres, but it can look at different types of concentric circles. So let's look at annuluses. This is a very, very popular topic in competition math and in very complex, high level math, complex math. Some things that you might be relating to or seeing in college courses. Even so, it's a very important thing to know about and to get ahead of the game. As an Enrichment and eCoreAcademy, we want to prepare you guys for those very situations. So let's look at the formula for annuluses. So an annulus is the region between two concentric circles, and all that concentric circles is basically when you take a singular circle and you wrap another circle around it. That's all it is. That's what concentric circles are. And to calculate an annulus, you use this formula. And all the formula is basically you're utilizing your area formula. So it's going to be pi r squared minus pi x squared. So you might be wondering, what is x? X is just another way of relating to the radius of a smaller circle. So this is an annulus right here. One large circle, and then you have one smaller circle. I'll trace that out here. Kind of make that a bit more noticeable. That's your annulus. You have a larger circle and then a smaller circle within, and you're trying to find out what the annulus is. The annulus is this distance here, right here. It's this distance outside between this smaller circle and this larger circle, this area of this whole thing here, this whole entire thing here. That's whatever I'm shading in here. That's what you're trying to discover the area for. Okay, so that's the area that we're trying to discover. Now, what I'm basically saying is r squared is going to be the radius. So you're going to have a common center here. They're going to share the same center between these two circles. The radius is going to be the radius of this larger circle, this whole circle, large circle here. And let's say, for example, that's 4. And then the smaller radius is going to be x, which is, in this case, let's say it's 2 from the distance of this smaller circle. That's going to be 2. So let's plug that into our equation here just to calculate. We're going to leave this in terms of pi just to get an exact answer here. Because we're dealing with a larger equation, we want to put it in exact terms. So we have 4 here, so we're going to plug that in. 4 squared minus pi times 2 squared. And I'll just write this down. Small and large. Just to identify that. So pi times 4 squared minus pi times 2 squared. So that's going to be 16 pi minus 4 pi, equals 12 pi. And that's the area of our annulus. All right, everyone. So that'll be it for today's video. I hope you guys enjoyed. Please make sure to smash the subscribe button, hit that like button on this video, as well as turning on post notifications so you don't miss out on any of our latest uploads. We will be posting a whole lot these upcoming months, and especially these upcoming years. So please support us and don't miss out on any of our content, and don't fall behind with our curriculum. Once again, we're here to help you. So please help us return that favor by hitting that like button, subscribing, and of course showing your support all throughout. Feel free to comment down below as well. Of course, we love our constructive feedback, and we really like hearing what our audience has to say. So we really appreciate that, and we wouldn't be here if it weren't for you all. Once again, please visit our website, like I said before, at www.ecoreacademy.org. There we have full unlocked access to what we as an online learning platform, e-learning platform, actually offer. So that is where we have everything that we actually offer and have developed as an online e-learning platform. There we have full unlocked access to integrated quizzes, worksheets, and note sheets that go along with each and every single one of our videos, organized into course studies and by lesson. We also have progress checks there, special events, tips and tricks there that are aside from our YouTube channel and our social medias there. We also have our contact information if you want to reach out to us. And if you haven't visited our website already, please, which you only need to make an account to get full unlocked access to what we offer at our website. But if you haven't already and you have a question, please email us at eCoreAcademy@gmail.com. You can ask us questions or just reach out to us if you'd like. And finally, please visit all of our social medias. Socials at Facebook, Twitter, and Instagram. We have our full links down there in the description box, so please check that after watching each and every video or before. And that's at Facebook, Twitter, and Instagram. You can see what kind of content we have there and use our mediums to share our videos. Once again, everyone, I hope you all enjoyed. This has been AJ Raj, and I will see you guys in the next one. Peace.